Points, here we go. You got to do two things with stationary points. Number one, you got to find them. And then you also have to determine their nature, right? So in terms of stationary points, sometimes these two get phrased in a different way. They'll say find turning points. Okay, can you see that finding turning points really amounts to doing these two things? You've got to find the stationary points, then you've got to determine the nature of the stationary points. And that'll tell you it's a max, or it's a min, or it's neither. Okay. So how do we find it? Okay, what do we do? Stationary points. Stationary points. What's the first thing we have to do? A stationary point is defined by, it's got a horizontal tangent, okay? So the gradient at that point is 0. So what you want to do is solve dy dx is equal to 0, okay? You solve that, you're going to find it. But secondly, if you want to actually find where the location of the point is, when you guys are ready. Do you want to ask a question? Or? Still ready. Still waiting. Still waiting. Okay. Solve. This will tell you the x coordinates where you've got a stationary point. But then you've got to do a little more legwork than that. You've got to actually pop it back into your original equation. Okay, and that'll give you the y coordinate. Okay. So sub back into y. And that'll give you the y coordinate. Okay? So there's two steps, then you've found them, okay? But if they're asking you to find turning points, or if they're asking you to determine the nature of those stationary points, which are really the same thing, you've got to go a little further. Okay? Now, by this point, because we know what the first and second derivative are, right? We now have two different ways, two different methods for determining the nature of a stationary point. Okay? So method one. Okay? What do? You want to test the first derivative on either side. Okay? Test dy and dx. Just to the left and just to the right. Okay? Now when you test, you want to pick values that, number one, are nice and easy for you, and number two, don't go too far past other stationary points. Okay? So you want to select values carefully. You know, for instance, if you found a stationary point at x equals 1, okay, to go to left and the right, excuse me, frog caught in my throat, you could just go just a little bit to the left, you know, 0.9, and just a little bit to the right, 1.1. And then probably give you some helpful values. But 0.9, 1.1, they're difficult, fiddly numbers to work with, so we probably want to pick numbers like, say, 0, or 2. So those are easy values, right? But in the same way, for instance, suppose I found a stationary point at 1 and a stationary point at 2. Okay? Well, then I can't pick 2 as a value to test on the right. I'd have to pick something in between, like say 1.5. Okay? So sometimes you can't get away from picking an annoying number because you have to be between stationary points. Okay? So select your values carefully. Then, once you've tested it, you'll have one of three conclusions. Okay? Number one, it'll be a local max. Okay? Because you go up, then across, and then down. Number two, it could be a local minimum. Okay? If you get the reverse. Or, what was the third alternative? A stationary point. What else could you have? Yeah, if you have a point of inflection at the same time, right, you're going to get a horizontal point of inflection, which is neither a minimum nor a maximum. So you can get this two ways. You can get up, across, up. That's a horizontal point of inflection. Or you could get down, across, down. Also a horizontal point of inflection. Okay? So when you test on either side, the first derivative will tell you any of these. Okay? So that's method one. What was our second way? Do you remember? This was the newer way, right? Concavity. Yeah, that's right. Use concavity. So find out if it's concave down or concave up. So what you want to do is, rather than test the first derivative on either side, you test the second derivative at that point. Okay? Okay? So at the stationary point as opposed to on either side. Yeah, of course. Alright, so therefore, you're going to get some conclusions from that, right? Depending on the value of the second derivative. If the second derivative is negative, okay, like so, what does that tell you? Negative second derivative. That means it's concave down, okay? So that's concave down. Which tells you it's which kind of point? That's a max, right? Okay, so there's the first option. If you got a positive second derivative, obviously everything is backwards. So you're concave up and you have a minimum. And now here's where you've got to be careful. If your second derivative, I've just run out of space here, so I'm just going to keep going over this side, okay? If your second derivative is 0, okay, what could that mean? Now remember, we've looked at counterexamples here, so you can't be dogmatic, right? What it means is you have a possible point of inflection. Possible. Okay? Now, if it's first derivative 0, second derivative 0, remember, it could be x to the 4 or x to the 6, so it may not be an actual horizontal point of inflection. So in this way, you can see when you contrast the two methods, right? Testing the first derivative tends to be a bit more laborious because you've got to test values and so on, okay? But it's more reliable because when you've got the values on either side, you know for sure it's a horizontal point of inflection or a max or min, okay? Here, you're like, well, maybe, okay? So if this is what you got first derivative 0, second derivative 0, what would you do next? How could you tell what it was? You could go to the third derivative. I'm going to try and avoid that because you can end up with similar problems, right? What I would do is you either resort back to this test, you go back to testing the first derivative on either side, and that'll tell you it's going down, across, down, horizontal point of inflection, or the reverse. Or, if you want to verify that it is a point of inflection, and this is getting to the next kind of critical point, how do I verify that something's a point of inflection? What does a point of inflection mean? It's a change in concavity, right? So I would then have to test the second derivative on either side. Okay? See, yeah. So you can see, when you get the second derivative being 0, okay, you've got to be careful. So you can't just say, oh, it looks like this, so I reckon. If they say prove that it's one or the other, you must test. You've got to use the second derivative, you've got to use the first one, you've got to do something. Okay? So this is stationary points. Remember, you've got two different methods. Generally, we like the second derivative, okay, because it tends to be faster. But you would avoid it if your fraction is rational. Sorry, if your function is rational. Do you remember why? Why do we want to avoid the second derivative? If you've got a rational function. Yeah, that's right. If you have something like, say, this. Okay, you differentiate once, because you're using the quotient rule, you're going to end up with another fraction, but worse. And then if you differentiate again to use the second derivative, it just keeps on getting worse and worse and worse. Not only does it get worse, your method is more error prone because it's more complicated. Okay, so you're more likely to get a bad result. Okay? Alright, that's stationary points.